So this is just the start of what differential equations is all about. It's just kind of an introduction to what differential equations is. Give you an idea of what they are. We're not going to solve any yet. We're just going to look at kind of what is a differential equation. All a differential equation is an equation that consists of derivatives of one or more independent variables. And so really, it's all about rates of change. We're looking at how do things change over time and see if we can't come up with models for those. There are many different types, there are two different types of differential equations. Usually we write DE for differential equation because we're too lazy to write differential equations. There's an ordinary DE or ODE. Again, we don't like to write things out too much. These involve only one independent variable and involves ordinary derivatives. In other words, just a regular derivative that you're used to. An example would be something like dy dx plus 3x equals 7y. This is a differential equation. It's an equation because there's an equal sign, and it's an equation because there's a dy dx. It's a differential equation because there's a dy dx as the derivatives. A partial differential equation, or PDEs, involve two or more independent variables. And this means it involves what we call partial derivatives. So this is where you might have two different things that are involved, two different variables that are involved in this. Like here, we have dy dx plus 7y equals 5 sine t. T and x are your independent variables. There's only one dependent variable, your y. So the question is, which one of these are ODEs and which ones are PDEs? So that's where we're going to start. So this is a differential equation, y double prime plus y prime minus 3y equals 5. When we write it this way, it is assumed, because of the notation we're doing, that it's a derivative of y with respect to whatever the one independent variable is. So that means that this one happens to be an ODE. Trying to get my thing to work. It's not working for me. All right, so this one is what we call an ODE. So we would write ODE on this. This one is the partial derivative of y with respect to t squared plus the partial derivative of y with respect to u plus 5 equals 7t. So in this case, this is actually the second partial derivative of y with respect to t. There's a t independent variable and there's a u independent variable. So there are two independent variables. There's still only one dependent variable, y, but there are two independent variables. So this is a PDE, partial differential equation. So this one is the third derivative of y with respect to x plus the derivative of y with respect to x plus 7y is equal to 3e to the x. Again, noticing here we only have one independent variable, just x. So this is an ODE. What we'd like to do is talk about what we call the order of the differential equation. The order is just what happens to be the highest derivative. So if you think about this, the order of a polynomial is your highest polynomial power. So this is kind of that same idea, is that your highest order of your derivative. So we also have some notation. The nth derivative, nth order differential equation means that we're taking a function. Basically, if you think about this, these are just all functions. We could actually write these all equal to 0, bring everything over to the other side, have them all equal to 0. And when we do that, we would then have basically a function is equal to 0. And so that's what this notation is about, is that we have some function that's a function of x, your y prime, your y double prime, all the way to your nth derivative of y equals 0. Another way you can also think of it is you could actually say that your nth derivative of y with respect to x is equal to a different function of x, y prime, y double prime, all the way to the nth minus 1 derivative of y. This is what we know as the normal form. Going back real fast to this very first one, let's talk about what the order of each one is. This first differential equation has a second derivative and a first derivative. So because it has a second derivative, we would call this second order. This one has a second partial derivative, a partial derivative. So this again is also second order because it has a second derivative. This one has a third derivative as its highest derivative, so this is a third order. We could again also rewrite these. I could actually solve this for the third derivative, get everything to the side, and that would be my normal form. Or I could solve and get all this equal to 0, bring the 5 over here and get this all equal to 0, and that would be the other form that I could have. So that would be your other notation. We can also talk about linearity. The nth order differential equation is what we call linear if f is linear in y. What that means is that your function, that function we were just talking about, is linear in terms of y. In other words, y doesn't have any products involved with y's and y primes. It doesn't have y is all linear, so there's not going to be any powers on the y's. There's no exponentials on the y's, just the y's. We don't care what the x's are doing. So we would actually think of having some function of x as a coefficient times the nth derivative, plus a different function of x times the n minus first derivative, all the way down to a different function times the second derivative, plus a different function of x times the first derivative, plus a constant of x times y is equal to some function, we call it g of x. Again, these are all these coefficients are functions of x, even this g of x is. So an example, 5x times y double prime plus 7 sine of x y prime plus e to the 4xy equals 7. This is an example of linear differential equation. And I realize that sine of x and e to the 4x are not linear, but those are x's, not the y's. There's no y times y prime. There's no e to the y. There's nothing with anything. All the y double primes and y primes are linear. So this first one is in fact linear. This second differential equation, 5y times y double prime plus 7y prime plus 3y equals 9. It looks like it's linear, but then I notice I have a y times y double prime. So I have y times its second derivative. So that makes it not linear. So this one is not linear. And whether something's linear or not linear depends on how we actually analyze it. That's why it's kind of important to have this understanding of this, what's going on. The next thing I want to mention is the solutions to a differential equation. We call it phi in this book. You can call it anything you want. It's just a way to write it. It's defined on some interval I, and it's the solution to the differential equation if it satisfies the equation. Think about it. If you have 3x plus 5 equals 7, the way, or let's say 3x plus 5 equals 8, let's get a little bit easier one. The way you know that x equals 1 satisfies it is when you put 1 into the equation, it actually satisfies the equation. It actually makes it true. Same thing here. You'd put that solution in and make sure it's true. Your interval, your I, is your interval of definition, or it's also sometimes called the interval of existence, sometimes the interval of validity, and sometimes just the domain of the solution. So you would look at those I's. Those I's are a little different than the domain of the function of the solution itself. So when you have a function, you have a solution, you have that function would have its domain. The I is actually a little bit different than that because I is actually going to be not just the domain of this function, but it's the domain of the solution. And what we mean by that is it's going to be over just, you're not going to have a discontinuous interval. You're not going to like do A and B or something like that. You're going to have both, just one section. So you'd have to look at that. So let's look at this example. Let's say we want to show that y equals 3 secant of x is a solution to y prime equals tangent of x times y equals 0. And we want to find the interval I for which it is defined. So let's go ahead and look at this. To go ahead and do this, we need to find out if this does in fact satisfy it, which means we take and plug it into this differential equation, which means I'm going to put the y in, 3 secant x in for y, but this I need y prime. So I need to find out what y prime is first. So y prime, the derivative of secant, is secant x times tangent x. All right. So then we're going to go ahead and put that in. And we want to know if, again, I like to be very specific with my work. So I'm taking y prime minus tangent of x times y equals 0. And I want to know if I plug in the 3 into the 3 secant x tangent x in for y prime, and the y was 3 secant x in for y, do I in fact get 0? Well, you can see you do, because you have 3 secant x tangent x minus 3 secant x tangent x, so we do get 0 equals 0. So, and you're going to have to start realizing that you need to be communicating to other people. You're not just doing this for me. You're not doing this for yourself. You're communicating to people. So you need to let people know what you found. You now know that 3 secant x tangent x equal to y is a solution. I'm sorry, that's the derivative. What the function was 3 secant x. So y equals 3 secant x is a solution. Two, y prime minus tangent x times y equal to 0. Now the next thing is we got to find that that interval. So let's go ahead and find that interval. So let's think about y equals secant x. Y equals 3 secant x. So let's think about secant x. What is its domain? So the domain of secant is, well, if you remember, secant is 1 over cosine. So is wherever cosine is 0 is where we have a problem. And so cosine of 0 is pi halves minus pi halves. So this would be minus pi halves to pi halves. That's not the only place. You can also have pi halves to 3 pi halves. And you could have 3 pi halves to 5 pi halves, and so forth. And I didn't go the other direction, but you can go the other way also. This isn't actually I. This is the domain of this function. But I is just one of these. I isn't over all of these things. It's not the same as the domain. It's actually just one of these areas. So you'd pick one of these. So we could say that I could be minus pi halves to pi halves. It could also be any of the other ones, but we're going to go with that one at the moment. And the way we tell which one it is it depends on if you have an initial value. What initial value is kind of a point that would give us information about that. And so you would do that one, and you could look at that. So usually it's when we have an initial value, when we know something, and that tells us which one we'd actually want, but we could just go with that at the moment. When we do these, in this occasion, when we did this, we had just y equals 3 secant x, just a single function. We know exactly where that function is. But we actually could solve a differential equation and get what we call a 1-parameter family of solutions. In other words, there's some constant in there, and it's called a 1-parameter family. If you happen to have a second-order differential equation, then you could have a 2-parameter family, and so forth. So it depends on what order you have, as how many parameters you have. Nth order would then have n parameter family of solutions. And so it's just some constant you might have, and then you go to try to find those constants if we have what we call an initial value problem. We have what we call a particular solution. This is when the solution is free of those arbitrary constants. So you wouldn't have a C in there. Your notation we use in this course is y sub p is what we call that particular solution. The general solution would just be y sub just the y value, whatever it happens to be. Our singular solution is a solution that's not a member of the family of solutions. And that can happen where you get a differential equation, you solve a differential equation, you get an answer, but that one isn't the only one that satisfies the differential equation, but you can't get any others from that. And those are what we call singular solutions. All right, I want to show that y equals c e to the t squared is a solution to y prime equals 2ty. This is actually a family of solutions. Y equals c e to the t squared. We have this constant in here. We have a one parameter family. We don't know what that constant is. We have that constant in there. And so we're going to find this. And remember that constant comes from, it's kind of the same idea of your derivatives. Your integrals, where you're taking an integral and you have that plus c. That's kind of where this comes from and what that idea is about. So we're going to go ahead and solve this. Again, what that means first is to plug it in. I first need to find the derivative. So I need to find the derivative of y. Constant is just a constant, so we're just going to have that c. The derivative of e to a power is, of course, e to the power, and then times the derivative of the power. So my derivative is 2ct e to the t squared. So what we want to know is when we plug that y prime in, does it satisfy y prime equals 2ty? So we're going to plug that y prime in, 2ct e to the t squared, and I want to know if that equals 2 times t times y, but remember y was c e to the t squared. Well, you can see that they do equal each other. It does check out. Everything's good. So y equals forgot what I had. Y equals c e to the t squared is a solution to the differential equation. All right. I do want to mention that sometimes some of our solutions we see in this course involve what we call the hyperbolic sine, hyperbolic cosine, hyperbolic tangent. I want to talk about what those are because you've not probably been exposed to those very often. The hyperbolic sine the symbol for it looks like a cinch. I hear people call it cinch, but it's S-I-N-H is what it actually is. So that's the symbol for it. Y equals the hyperbolic sine of x. It actually comes to us from, the reason it's called a hyperbolic sine is sine, cosine, and tangent are defined on a circle. The hyperbolic sine, cosine, and tangent are defined on the positive part of a hyperbola. So that's where this comes from and why it's called a hyperbolic sine. It happens to be actually equal to e to the x minus e to the negative x over 2. So that's actually what the hyperbolic sine is. The hyperbolic cosine. The symbol for that is COS, like cosine with an H on it. So some people like to call it cosh. So you'll see that one. And the hyperbolic cosine is e to the x plus e to the minus x over 2. And then the hyperbolic tangent and I don't have a great name for that one. We call them cinch and cosh, but hyperbolic tangent is just tan with an H on it. I don't have a name for it. So it's just a hyperbolic tangent. And the hyperbolic tangent is e to the x minus e to the negative x over top of e to the x plus e to the negative x. So if you notice, if you took the hyperbolic sine and plugged it over top of the hyperbolic cosine, you would get this. So it actually is the hyperbolic sine divided by the hyperbolic cosine, which makes sense because tangent is sine of a cosine. So hyperbolic tangent makes sense to be hyperbolic sine over hyperbolic cosine. So you might see us use these formulas in the book, in the course. Sometimes they become useful to use just to make things easier, because we will probably see e to the x plus e to the negative x over 2 as a solution, and it's easier to write that as a hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. The derivative of hyperbolic sine is hyperbolic cosine. So they're not exactly the same as sine and cosine, because the derivative of cosine, of course, is negative sine, but they're very, very close. The last thing I just want to mention in this section is we can also talk about systems of different ODEs. This course, by the way, will be only dealing with ODEs. PDEs become very, very complicated, and usually that's more of a standalone course by itself or a graduate level course. So we're only going to be talking about ODEs and systems of ODEs in this course. And what this means is we actually have two dependent variables, x and y, and then they would be, the derivatives of x would be involved with a function of t, x, and y, where t is your independent variable. And then you have the derivative of y with respect to t is some different function of t, x, and y. Your solutions would be some function of t for x and a different function of t for y. Both are defined on some interval I, and both satisfy the system. Unlike systems of equations that you've seen in algebra classes, the problem is that your solutions here are not necessarily unique. So you won't always see unique solutions to these. They're equivalent to each other, but they're not unique. And so that's kind of an introduction to what differential equations are about, and we will move from there.